And the last of our shapes are when we have got 6 regions of electron density around the central atom. So that's going to give us an octahedral electron cloud, and if all 6 of those regions are bonding pairs of electrons, something like SF6, then our shape is octahedral. But there are, of course, lots of other versions of this, and you'll see that 2 of them are exactly the same as with 5 regions, so there's no new shapes to learn there, luckily. When there's only 2 bound to the central atom, and therefore in this case 4 regions of electron density that are lone pairs, then those 4 are the ones that are sort of sitting around the plane. So what will happen there is that these 2 will be pushed away from each other to create our linear structure. Those 4 electrons there, just so you're aware, you've got 1, so you've got 2 going into the board, 1 up and 1 down, and 1 coming out, 1 up and 1 down. So that's actually, they're not sitting on a plane like this. And it's hard to show on a whiteboard, but there's 2 coming out like that. Start again. 2 coming out like that, and 2 going into the board like, how to do this without my hand getting in the way, 2 going into the board a bit like that. All right, so that's your linear shape there. If we turn one of those lone pairs into a bonding pair, doesn't matter which one, then we get those 2 are still together, and we get 1 going into the board and down. Well, if I rotate that in space, it creates the letter T again, just like with 5 regions, where we have 3 bonding pairs creating a T-shaped. So it's hard to show that way there, but this is kind of what I'm trying to show there. 2 in the same plane, 1 going into the board, and then if I rotate that, I end up with my T-shape. You'll remember, hopefully, with 5 regions, when you had 4 bonding pairs, you got a seesaw shape. Well, in this case, that's not the most stable arrangement. It's not going to give the most repulsion possible. The highest amount of repulsion you're actually going to get is if the lone pairs are the ones up and down. So the axial ones, the up and down. So these 2 would be the lone pairs, so they're gone now. Therefore, for the others to get as far away from each other as possible, they'd be arranged in space like that, with 90-degree angles between each of them. Because we've still got a lone pair here pushing them down, a lone pair underneath pushing them up, so it'll sit nice and flat on a plane, on a bit of paper. So we call that square, because that was the shape it made, planar, because it sits on a flat surface. You could draw these all as straight lines, but that would mean you've got a lone pair on the top and a lone pair on the bottom. So the convention is you show 2 of them coming out of the board and 2 of them going into the board. So that's 2 going into the board would be like that at 90 degrees from each other, 2 coming out of the board at 90 degrees like that. All the 180 degrees, because it's 90 plus 90, between those ones that are opposite. And then the last one is, if we've got this being square planar, the next bonding pair would just be stuck right on top. So if we've got a square, and then we put 1 on top, then it creates a pyramid, just like the pyramids in Giza, and so on. It's got a square base, and it's a pyramid. So we call it a square-based pyramidal shape. So with this one, there are 2 new ones, here and here, and they're both based around it having a square around them. So that's the new thing. 6 regions, you start to get these squares. Octahedral is our shape, because actually if you drew lines around the outside, it's an 8-sided object. So there we are. That's all of the new shapes. Remember, what you're going to be doing is looking at your ion or molecule's Lewis structure, looking at how many regions of electron density it has around it. If it's 6, you then have to look how many atoms about it, 2, 3, 4, or 5, or 6, and then infer the shape from those things there.